yesterday we said that a second order system consists of a resistance and two energy storage elements, namely inductance and capacitance. So this is a typical second order system. In fact, if we give an initial condition for the inductance or capacitance, then we don't even have to have the source, but currently I have included the source. And we started by writing the equation that L di by dt plus Ri plus 1 by C integral I dt equal to BDC. And on differentiating this equation, we wrote this as L d square I by dt square plus R di by dt plus I by C equal to 0. And we wanted to bring L down. So what we did was we removed this L from here and then we wrote this as R by L and I by LC. And we said because the second order derivative, the first order derivative as well as I, all of them are in the same equation here. So the possible solution could be A times e power some st. So this could be a possible solution for I. That's what we said. So we wrote this as basically substituting this for I, we said A e power st multiplied by s square, right? Plus we said R by L multiplied by again A e power st, and then we multiplied basically di by dt will give me s, and we said this is A e power st divided by LC equal to 0. Then what we did was we divided, I'm just recapturing whatever we did yesterday. So this, when we do, we got something called the characteristic equation, which was s square plus s R by L plus 1 by LC equal to 0. So this we called as the characteristic equation of the system. So this equation, when we solve for, we will get S equal to, we can write S equal to minus R by L plus or minus root of R square divided by L square, and we said 1 by LC multiplied by 4. So instead of writing divide by 2, we had included the 2 here. So we said R square by 4 L square, and instead of 4 and 4 it got cancelled, so we said 1 by LC. So this will give us basically two solutions, S1 and S2, and we talked about 3 cases here. One is the over-damped system where we are going to have S1, S2, they are distinct real roots. So when we talk about distinct real roots, we are essentially talking about R divided by 2L is going to be greater than, not R divided by 2L, right? So this is R divided by 2L here. So 4L square, sorry, this is going to be R divided by 4L square, that got erased. So R divided by 2L is going to be 1 by root LC. This is the first case we talked about, and we wrote this solution as A1 e power S1 t plus A2 e power S2 t, where S1 and S2 are minus 2 by R by 2L plus R minus root of R square minus 4L square by 1 by LC. So these two are going to be distinct because this is going to be a positive number. Whatever we have under root, this is going to be a positive number. So what we get will be plus or minus a square root of that positive number, right? So this we called as over-damped system. Generally, the response for this would be in such a way that if we are looking at the current, it might start from 0. It will probably, if the initial condition is 0, of course, and it might reach a particular value and then die down eventually. This is the way it is going to be. So this is essentially the kind of response we would see for over-damped system. The next type of response is when I'm going to have this, the second response is generally known as critically damped, which hardly ever happens in nature because you have to have exactly S1 and S2 are not distinct, but they are real. They are not distinct, they are one and the same, but real. So this is going to be when R by 2L is equal to 1 by root LC, which means whatever is under root, that is going to essentially, become 0, because of which we are going to have minus R by 2L plus or minus 0. So both of them are exactly going to be one and the same. The generalized solution for this will be something like A1 plus A2 T multiplied by e power st, where S1 and S2 equal to S also. So in this particular case, we are going to have S1 equal to S2, which is equal to S. They are not distinct. And the third type of solution what we have is underdamped condition, where we are going to have the square under the square root, whatever we have, that is going to be a negative number, because of which we are going to have this in the form of alpha minus alpha plus or minus j beta, where this j is actually root of minus 1. So this is the kind of solution we are going to have, and we are going to have R divided by 2L less than 1 by root LC. So what we have under root is a negative number. So that is the reason why we are getting imaginary roots, and this is going to result in the solution, which is going to be something like, if I say this is alpha and beta, so I'm going to have a e power, rather I don't even have to mention a constant here, I should say e power minus alpha t multiplied by say a1 cos beta t plus a2 sine beta t. Okay, so this is going to be the underdamped system, and underdamped system response is going to be somewhat like this. I will have the current increasing and probably overshooting, and then it will go through a sinusoidal oscillation. In fact, finally, if it is going to settle down at 0 value, I should show it somewhat like this. It is starting from 0 and it overshoots, and then I'm going to have this ultimately settling down like this. This is going to be the kind of response we are going to have for underdamped system. So in this particular case, very clearly, if the resistance is quite high, then this in all probability will not be possible, because if the resistance is low, in all probability this, when the resistance is larger, in all probability it will show an overdamped response. But when it is transitioning from overdamped to underdamped or vice versa, it might just go through the critically damped point. So this is the crux of what we discussed yesterday. So what I'm going to do now is to simulate at least one overdamped system and one underdamped system, and let's try to look at the response. So I'm going to do this in a computer simulation package called PSIM. So what I'm going to use here is the package called PSIM. So this you can also download as I told you yesterday, PSIM students version you can try to download, which is available free of cost, or you can try to download LT Spice. So let us try to now, I'm going to look at PSIM. So let me take PSIM. So here is the package which I have already downloaded and kept. So I'm going to essentially open this package. Okay. And I'm going to create a new circuit. Okay. And I'm going to just take a voltage source, place it here. I'm going to take a resistance, place it here. I'm going to take an inductance, again place it here. Later on I can connect, and I'm going to take a capacitance and place it here. So let's say I am connecting this here. I'm connecting this here, and I want to see the current because that is what is going to give me the response. So I'm going to take the current. Ammeter, this is like an ammeter. You can see that this is the ammeter that I have taken, and I'm going to connect it like this, and I can connect this here. Okay, fine. Now what I'm going to do is to assign values. So I have taken one system where I'm taking this resistance to be, say, 5 ohms. Okay, so I'm going to show this as 5 ohms. So you can see this is showing as 5 ohms. And I am taking the inductance to be 0.5 Henry. So this 0.5 will also display here. Okay. And I am taking the capacitance to be 0.125 Farad, extremely large values. I'm just taking it for the heck of it. So I'm going to take this value. So this particular ammeter I will call as just I. This is the current that I'm going to see. So I'm going to call this current ammeter measurement, whatever block, I'm going to call this as I. Okay. Now I will take this value. If I actually take this value as some 2 volts or 1 volt, whatever, doesn't matter. Okay, let me take this as 2 volts. And let me try to run this system. I'm not taking any initial condition. I have taken no initial condition. Initial current is 0. And this initial voltage is also 0. Okay. So let me try to run this. But before running, I have to give some control. So let me try to calculate the values corresponding to L and C. L is 0.5 Henry. So let me run this for say 4 or 5 seconds. Doesn't matter. 4 seconds let me run it for. But let me try to look at the L value is 0.5 Henry and this is 0.125. So let me go back here. And if I want to calculate for this system, I have taken example system 1. I have taken R to be 5 ohm, L to be 0.5 Henry, and C to be 0.125 Farad. So let's try to calculate what is 1 by root of LC. Okay, so this is going to be 1 divided by 0.5 multiplied by 0.125 is 1 by 8. So I'm looking at this. How much is it? This is 1 by 2, isn't it? This is 1 by 2. So 1 by 2, that is 1 by 16. So I'm going to have 1 divided by root of 1 by 16. So that is essentially going to be 4, right? So I'm going to have 1. This is going to be 4. Is that so? Right? So this is going to be 4. And what is R? R is 5. So There is something wrong. R by 2L is how much? R divided by 2L. This is essentially 5 divided by 2 multiplied by 0.5, which is 1. So this is 5 itself. So R by 2L happens to be greater than 1 by root LC. So this should come out to be an overdamped system. Okay, so let us try to look at the response, what we are getting from this particular simulation. So this I am trying to run it for 4 seconds. So let me try to simulate, run simulation. So it is running the simulation. So this is the kind of output it is showing. Can you see? So it is starting from 0 and the current is going up to something like greater than 0.3 and then it is coming down to 0 finally. When I run it for so many milliseconds, you can see the time is shown in millisecond and this is coming down to 0, which is like an overdamped system. Okay. Now let me try to look at this with again some kind of initial condition and 0 voltage. So let me make this voltage as 0 and let me take the initial condition. So the initial condition I am taking here as maybe 1 ampere and I'm taking this capacitance initial condition something like 2 volts. Okay. So let me try to run this once again and see what happens. See, it has initially gone with some 1 ampere of current and it has gone through an oscillation up till -4 ampere of current and it has come down to 0. The -4 ampere might have been instigated by the capacitance unless we sit and solve the entire thing because there are 2 exponentials. Please remember what we wrote earlier. So we got basically 2 exponentials, summation of 2 exponential we are saying, which is a1 e power s1t and a2 e power s2t. So both of them put together, what kind of exponential response it gives, that is kind of difficult to say. So that is the reason why we are starting from 1 ampere, which was the initial condition we had given for the current, and it is addition of 2 exponentials and ultimately it is coming down to 0. Let me try to get the sense for an underdamped system. So for an underdamped system, what I had taken again the values based on one of the examples. So this I'm taking as 14 volts. Okay. And I'm taking the resistance to be 2 ohms. And I had taken the inductance in this particular case to be rather than 0.5, I have taken 1 Henry and no initial condition, no initial current. And the capacitance I have taken as 0.02. Let's calculate again for this. Okay, so let me try to go back here and calculate this for example 2. So let me take this values for example 2. So what am I having here? R is VDC is 14 volts. R is 2 ohm. L is 1 Henry. And C is 0.02 farad. So let's calculate first of all 1 by LC. 1 by LC is going to be 1 divided by this is L is 1 and this is 0.02. Okay, so how much is it? 50. So this is going to come out to be this will come out to be 50 and you are going to have R divided by 2L, if I try to calculate in this case, R is 2 ohms and 1 by 2L, so this is 2, so I'm getting this as 1. So R by 2L very clearly is less than 1 by LC. So if I try to look at what is R divided by R square.
Mom, to check
Yeah.
under root LC, right?
Yeah.
1 by under root LC, right?
Yeah. So R by 4L square is subtract from this you are trying to subtract 1 by LC. That's what we were trying to do. If you look at the under root, this is essentially R square divided by 4L square minus 1 by LC. Okay, so if we do R square by 4L square minus 1 by LC, that is going to be a negative number. Instead, I have to say 50 minus 1, which is equal to 49. So I'm going to have minus root of 49. This is what I'm getting. So which will be plus or minus 7i. What I would get will be 7i. I'm going to write this as j, not I, because I is current. So I'm going to write this as plus or minus 7j. So what I am having is r by 2l, which is 1 plus or minus 7j. This is what I am getting as minus r by 2l. So this is what I am getting as S1 comma S2 in this particular case. So this is clearly an underdamped case. Okay, you get my point? So let us try to see what happens when I try to simulate this. So let me try to, this is 2 ohm, 1 Henry and 0.02 Farad. So let me try to simulate this. Oh. One or more fields are empty. Did I not give the value as 1 Henry? Let me see. I have given this to be 1 Henry. Okay. So initial current I didn't give anything. That is the reason why it is complaining. So let me try to simulate this. So you can see this is a sinusoidal response. So it is starting with some value which is actually going to quite a high value and eventually it is coming down. That is because if I try to join all the peak points of the sinusoid, it will be actually exponentially decaying curve. So this essentially gives us an exponentially decaying sinusoidal or cosinusoidal curve. The peak of the sine or cosine is decaying gradually, and the way in which it is decaying is exponential decay. And if you look at what is the time duration for one cycle of this, so it is starting from 0 and it is slightly less than 1 second, it looks like. So we will have the time period given normally by 1 by root LC divided by 2 pi. So 1 by 2 pi root LC. In this particular case, if I try to write it again, so I'm going to have this particular thing as 1 by 2 pi root LC will be generally given by the time or the frequency of oscillation. This is roughly going to be the frequency of oscillation of this sine wave. So this is going to be roughly the frequency of oscillation of the sine wave. Okay. So we can actually solve this particular problem. For example, let me first take the overdamped case and try to solve it.
Ma'am, can you please go back to the last page?
The simulation?
Yeah, no,
Or this?
just the notes, yeah.
Yeah.
Just a little up.
Yeah. Yes.
Ma'am, where the graphs were drawn on the left side corner.
Yeah.
The second graph, ma'am, can you please explain this one once again?
See, basically, this is showing A e power, let me go back to the expression here. So this is going to be e power minus alpha t. Alpha is r by 2l. And this, whatever we have got, is the sinusoidal function, which is cosinusoidal plus sinusoidal, which is essentially because of the Euler's formula, what we discussed yesterday. Saying that we are going to have e power minus alpha plus or minus j beta t. This is what we were getting as the expression. This j is essentially because of square root of a minus number, right? And the square root of minus number, when we write, we should have written square root of minus 1, which is I, which we are specifying as j. So e power minus j, any quantity, say theta, that has to be essentially written as cos theta plus or minus j sine theta. So if I'm saying plus or minus here, I'm going to have plus or minus here as well. So this is essentially Euler's formula. So here what we have is e power plus or minus j beta. So because we are having plus or minus j beta, we are writing cos beta t and sine beta t. So we are going to essentially have this to be, we expanded this yesterday, saying that, this particular beta and e power plus or minus j theta, when we write, we are going to get cos beta t and cos sine beta t with the j. So we actually said this as a1 plus a2 multiplied by cos beta t, and then we had another one as a1 minus a2 multiplied by j sine beta t. This is what we had basically, right? So because of this, we said that this entire thing we are taking as one constant, and this entire thing we are taking as another constant. So those two things I have specified here as, maybe you can say as a1 dash and a2 dash. So we are having basically a sinusoidal and cosinusoidal function here. But if I write this as, let us say, a1 some cos beta t plus a2 sine beta t, if I write a1 as some, this can be written as sine a cos b plus cos a sine b. So if a1 I am writing this as some sine theta, and a2 if I am writing as some cos theta, okay, or sine phi and cos phi. So this is in the form of sine phi cos beta t and cos phi sine beta t. So I can write this as some sine of beta t plus or minus theta or plus theta, whatever. Okay, so where I can write this as a1 equal to sine phi and a2 equal to cos phi. Right? So I should be able to find out exactly what is the value of phi also by saying tan inverse of a1 by a2 will be my phi. So I can say tan inverse of a1 by a2 will be my phi value. That will be equal to phi value. So I am showing this as a sinusoidal function ultimately. So I should be able to write this as e power minus alpha t multiplied by sine of beta t plus some phi, where this phi is determined by the constants a1 and a2. So this clearly tells me this is a sinusoidal function, but whose peak is exponentially decaying. You get my point? So I should be able to write this as, that's why if I try to look at it, it is an exponentially decaying sinusoidal function. So the peak is basically decaying exponentially. And that's what you see here also. The response what we have got. So if I try to look at this, this is exponentially decaying and ultimately becoming zero. If I had simulated it for longer, it would have ultimately decayed to zero. let me probably simulate this for a little longer rather than simulating it for only 4 seconds. If I try to simulate it for, it will take a little longer, doesn't matter, 8 seconds. Let me try to simulate it. It's running the simulation. You can see it is ultimately decaying to 0. So even if I had probably done it for just 6 seconds, it would have shown almost settling down to 0. Does this answer your question?
Yes, ma'am. Yes, ma'am. Yeah, I
Okay.
got it.
So basically what we are trying to say is there are 3 cases of solution where we are going to have either overdamped or underdamped or critically damped. And critically damped case is not very commonly encountered because it is only when you are transitioning from one case to another. We can in fact, yeah.
Ma'am,
Yes.
nothing. In overdam systems, you had shown another graph which went almost the opposite way. Like it took a dip and then it became stable. I didn't get that graph.
Let's go back to the simulation. Let me again put the values. I'm going to say this is 5 ohm. And I'm going to say this is 0.5 Henry. I think.
0.5.
Yeah,
Yes.
that's what I remember. 0.5. And the capacitor was 0.125, I suppose, right? 1/8. That's what we said. 125. Right? Okay. So let me try to again do this simulation. This is still 8 seconds. Let it be 8 seconds. Doesn't matter. So let me try to do the simulation. So here it is going all the way, maybe until 1.75 amperes or something like that, and then it is dying down to 0. When I didn't give any initial condition whatsoever. I didn't give any initial condition in this. So that's why I wanted to solve this actually. So let me try to solve this. What was the voltage I had given here? I had given this voltage to be 14 volts. Okay, and I didn't give any initial condition whatsoever. So let's try to see that. Let me go back here. So let me do this actually theoretically. Let's try to do it analytically. R is 5 ohm, L is 0.5 Henry, and C is 0.125 Farad. Okay, all these values are enormously high. Normally, we are not going to have such high capacitances visualized because generally capacitance is epsilon A divided by D, the distance between the capacitor. And you will generally have this area to be enormously high if I want such a big capacitance to be constructed. So it's not going to be very easy to construct such a large capacitor. Anyway, so R by 2L in this particular case will be 5 divided by 2 multiplied by 0.5, which is going to be 5 itself, right? And 1 by root LC is going to be how much? 1 divided by root LC is 0.5 multiplied by 0.125, which is 1 by 8, right? So 1 by 2, 1 by 8, this is going to be 4. 1 by root LC is 4. So this is R square divided by 4L square, which is 25 in this particular case. That is definitely greater than 1 by LC. That is for sure. Okay. So this is overdamped case. So let's try to first of all get what is S1 and S2. So S1 and S2 are minus R by 2L plus R minus root of R square. This is R square by 4L square minus LC, 1 by LC. How much is this? This is 25 and that is 16. So that will be the difference is 9. So I'm going to have this as minus 5 plus R minus square root of 9, which is 3. right? So I'm going to have two of them as the solution. One is -8 and the other one is -5 plus 3, which is -2. So I will get essentially a e power -8t plus b e power -2t. This is going to be the solution for I of t. Is this clear? Any questions on this?
No, ma'am.
Okay. So if we say that the initial condition I will assume I of 0 is 0. And let me say VC capacitance voltage is also 0. I have not taken any initial condition for capacitance voltage as well as inductance current. Okay. So let me try to see what this is. I of 0 is 0. I should say A e power 0 plus B e power 0, which is I of 0 is equal to 0. So which means A plus B is 0 for this initial condition. So this capacitance initial condition I have already, inductance current initial condition I have already taken care of. Now VC of 0, how do I get? I have to write basically 1 by C integral I dt is VC, right? And VC of 0, if I want to calculate, I should say 1 by C integral of A e power -8t plus B e power -2t, right? This is what I have to calculate. So this will be this 1 by C, that is 1 by 8, which is 8. I have to get this as 8 multiplied by, I should say, A minus 8A. Is it minus 8A? So, no, A divided by minus 8, isn't it? The first term will be A divided by -8 multiplied by e power -8t plus B divided by -2 multiplied by e power -2t, right? This is going to be the integral. So this is essentially VC of 0 is going to be equal to 0, we said. So I have to make this e power -0. This will also be e power -0. So I should say A minus A, this is, and this is going to be 4B, right? So this is minus 4B, right? That is equal to 0. Am I correct? Is this okay? So I'm basically calling this as 1. This becomes 1. This will also be 1 at time t equal to 0. So this is 8 by 8, which is minus A, and 8 by 2, which is minus 4. So this is minus A minus 4B equal to 0. So A plus 4B equal to 0, and A plus B is also equal to 0. Hi, what kind of solution are we getting? What kind of solution is this? VC is 0. This is also 0. And what are we getting this as? A. So if I try to look at both of them will come out to be 0. There is something seriously wrong. Have I made any mistake? Look at this. VC of 0 is 0. That's fine. Should we have some initial condition plus some constant? There is no constant here because A and B only you want to solve for.
While integrating, do we get any constant here, ma'am? Constant of integration.
Should we have a constant of integration which is C1? If I just simply say C1, so A plus 4B. See, in that case, you are having 3 unknowns and 2 equations, which you would not be able to solve for. Which you would not be able to solve for. Definitely not. So, have we made any mistake? A plus 4B is 0 and A plus B is also 0. If I try to simply subtract one from the other, I'm going to get again 3b equal to 0, which is b equal to 0. If b is 0, then a is also 0. No, there is something the matter. If I take an initial condition, then it's easier to solve. So if I try to take an initial condition in this, saying that what I had done earlier, remember? We had just given the initial current to be some 1 ampere, right? And I had taken the initial voltage to be some 2 volts. Here I have taken the initial condition as 2 volts. That's the problem. Whatever solution we got is with an initial condition. Okay. So let's do one thing with this initial condition, of 2 volts and 1 ampere. If I try to solve the same thing, let's try to solve this with an initial condition of 1 ampere and 2 volts. Let's try to solve this. So I'm going to say I of 0 is 1 and VC of 0 is 2 volts. Now we can say A plus B is 1, not 0. A plus B is 1 and A plus 4B is minus A minus 4B is 2. That's what we got. Minus A minus 4B is 2. Will this work? Let's see. So A plus 4B is minus 2 and A plus B is 1. So if we do this, we should say, if we subtract one from the other, I'm going to get A minus A 0, 4 minus 4B minus, this is minus 2 minus 1, which is minus 3. So B is coming out to be minus 1. Am I right? B is coming out to be minus 1, from which I can say A plus B is equal to 1. So A is going to be 1 minus B. So 1 minus minus 1, which is 2. Am I correct? So I'm going to get the solution to be 2 e power minus 8t plus minus 1 e power minus 2t. So this comes out to be all right. So in which case, see, probably we are negating the condition itself. Initial equation when we write V, which is 14 volts, equal to Ri plus L di by dt plus 1 by C integral I dt with an initial value of capacitance voltage also. In which case, maybe we are not even satisfying the original equation when we say I equal to 0 and Vc equal to 0. Maybe Vc of 0 equal to 0. That is the reason why we are not getting a proper solution. So this is the solution that comes for I of t when we are assuming the initial conditions like this. In which case, maybe we will get this, the solution what we get here. Array, why is this stuck here? So this is going to be, if we run this, let's run this, simulate, run simulation. So this was with initial value of current as well as voltage, and this is coming out to be, it is coming from 1 and it is reaching certain value and then it is coming out to be 0. Capacitance also has an initial condition and the current also has an initial condition. So unless we plot these two separately by again writing some kind of code, it is difficult to say whether it is exactly matching with what we have got as the current. Okay, so anyway, I hope you get the sense of how to